Okay, let's talk about coefficient of restitution. I don't know, I don't need my headphones on, but let me take them off. So the coefficient of restitution, we talked about this a little bit in class, but not heavily. It's a measure of how bouncy something like. So restitution in this case means like when the object's like compressed, like squished like a ball, like it's compressed, how much it wants to like push back, spring back to its original state. Okay, and that happens in a collision. Now, the reason why the coefficient restitution formula exists is I don't know exactly where it comes from, or I've never bothered trying to drive it. It's not hugely important, but basically, it's v final of object 1 minus v final of object 2 divided by v initial of 2 minus v initial of 1. Okay, so it's like the reverse differences between them. And notice that sometimes one of these will be negative, and then you're like adding them, right? So what is the coefficient of restitution? It's a measure of how bouncy an object is, right? That's what it is. It's a measure of how bouncy the collision is between the two objects. In theory, it should be about the same for two objects, or should always be about the same for two objects, right? Like much like coefficient of friction is always the same between two objects, doesn't matter what's happening. In this case, it's less accurate. It does seem that if you change the impact speed by a lot, it might vary a little bit. But our first lab is going to be based on trying to prove whether this is the case or not. All right, we'll find out. Okay, so let's do a couple. And basically means that the coefficient of restitution of 1, that means no kinetic energy is lost. It means the initial is equal to the final. Okay, less than 1 means kinetic energy is lost. Greater than 1 means kinetic energy is gained. I want to be very clear about this. If the coefficient of restitution is 0, that does not mean that kinetic energy final is 0. It might, but it does not guarantee it. Okay, and so we're going to look at this, how the coefficient of restitution varies based on a bunch of collisions. So we're going to look at the same collision 5 times with different outcomes. We're going to do 2 of them together, and 3 of them I've done already, and we will just skim over what we learned there, and then we'll bring it all together and compare the 5 situations. Okay, so example 3. We've got a 2 kilogram block moving right at 20 meters per second. So 2 moving right 20 meters per second. And we've got a 3 kilogram block moving right at 2 meters per second. And this is the before. And then after, my 2 kilogram block is moving right at 6 meters per second. And my 3 kilogram block has a velocity that I don't know. Okay, and I want to know what the coefficient of restitution of the collision is, but I need to know all 4 velocities, the initials and the finals, before I can do this. So I only know 3 of them. The way I find that is with momentum conservation, right? So I have momentum initial equals momentum final. That's 2, right, for the first object, times 20, plus 3 times 2, and that's equal to 2 times 6 plus 3 times our unknown v final. 46 equals 12 plus 3v final, and my v final is going to be 11.33. That means my coefficient of restitution is, I'm actually going to do this object as my first one, so my 3 kilogram one is my first thing, so it's going to be, it's going to be v final of the 3 kilogram one minus v final of the 2 kilogram one over v initial of the 2 kilogram minus v initial of the 3 kilogram. So that's going to be 11.33 minus, v final of the second one was 6 over 20 minus 2. This comes out to be about 0.3. Okay. Now let's consider the kinetic energy, just for good measure. Kinetic energy initial, see how that relates. This is going to be 1/2 times 2 times 20 squared plus 1/2 times 3 times 2 squared. Comes out to be 406 joules. Kinetic energy final, we can do the same thing as 1/2 times 2 times 6 squared plus 1/2 times 3 times 11.33 squared. And that's going to come out to be 228.6. Okay, so we lost kinetic energy, and our coefficient restitution is 0.3. Does that make sense? I don't really know what 0.3 means that I get 226 left, but sure, whatever. All right, so let's do it again. This time, I should really copy if I'm smart here. Same basic setup. Only difference is it's not 6 meters per second anymore. This time it is 8 meters per second. Okay, same idea. Momentum initial equals momentum final. I already know the momentum addition. We already calculated. It's 46, right? It's the same initial conditions. This is equal to 2 times 8 plus 3 times V. And I'm going to get my V final here. Final is equal to 10. Okay. Coefficient of restitution is going to be 10 minus 8 over 20 minus 2. This is 1 over 9 or 0.111. And kinetic energy initial, still 406, right? Because again, the initial stuff did not change from the last problem. And kinetic energy final is equal to 1/2 times 2 times 8 squared plus 1/2 times 3 times 10 squared. And that is equal to 214. Okay, so an even smaller. We dropped a bunch there, but it's even smaller kinetic energy, right? Last time it was 228, now it's 214. All right, so I did that 3 more times, this time where the blocks stick together, and I didn't bother showing kinetic energy initial. But the blocks stick together, you'll notice that the same final velocity, so the coefficient of restitution is always 0. All right, and the kinetic energy final is there. And then I did it for if the 2 kilogram actually bounce back a little bit at negative 1.5 meters per second, so left. Okay, so moving left at 1.5, which makes it a negative. Now, what was the coefficient of restitution of that collision? And it's close. It's 0.99. So this is almost elastic. It's so close. We see the kinetic energy final is 402. And I did one sort of in the middle. This time the 2 kilogram block is moving right at 2 meters per second. What is the coefficient of restitution of the collision? Again, velocity final 14. This gives me 6.7, 298. So to summarize that, this is the outcome of this 2 kilogram block. So the first one, they stick together, which is a V final of 9.2. All right, and then we have 8 and 6 to negative 1.5. So we go steadily down. And here, the kinetic energy initial is the same in all 5 cases. Kinetic energy final difference is 211, 214, 229, 298, and 402. And this is the CoR, 0.111, 0.3, 0.67, 0.99. And so what I want to point out here is there doesn't seem to be like the same change every time. Like from kinetic energy only rises by 3 total, and you go from 0 to 0.11. Meanwhile, here the kinetic energy rises by like 104, and you go from 0.67 to 0.99. Right? So it's a huge jump in kinetic energy for not that big a jump in the coefficient of restitution. All right, and in fact, like this, right, from here to here, it's a 0.37. From here to here, it's a 0.32. And this is a jump of 70, and this is a jump of 100. So it doesn't, like, there's no pattern to it. There's a pattern to it. Kinetic energy final, it gets bigger and bigger as coefficient of restitution gets bigger and bigger. But it's not 1-to-1. You cannot, like, sort of guess what the coefficient of restitution is very well, or approximate it by using the kinetic energy final. You actually have to solve for it. Okay? All right, that is all.